Morning, everyone. So this morning I wanted to start my presentation with a quote that I found a couple of months ago. It says, feeling gratitude and not expressing it is like wrapping a present and not giving it. So this morning I wanted to take a minute to thank Keith for this conference. 10 years is a big milestone, so congratulations for this. And I wanted to express my gratitude because you're allowing us to come here, share some of our knowledge, but you also, without knowing it, you're also creating a lot of deep human connections between all of us. And so I just wanted to say thank you for that. Okay, so my presentation is about the math behind PHY rates. And so we're going to try to answer this question: how are Wi-Fi data rates calculated? And usually when we talk about, or when we think about math, we either think about something very simple, like grade 1 type of math, or we think about something very complex. And looking at the MCS table, we would be tempted to think that calculating Wi-Fi data rates is something that's very complex. But is it really? Right? Is it rocket science? I guess we'll see. We'll see in a bit. But I would argue that it's not really rocket science. It's just science. Okay, so we're going to try to spend a few minutes here to try to kind of understand how all of these numbers are coming up and being calculated, and we're going to try to look at this formula in a little bit more detail this morning. And before that, I wanted to talk a little bit about the analogy between the road and the Wi-Fi. I know that's something we use a lot to explain Wi-Fi concepts. We have a lot of similarities between the road, what's happening on the road, what's happening on the Wi-Fi. And so here, to kind of introduce some of the vocabulary we're going to use to understand the Wi-Fi data rates, I wanted to kind of go over that a little bit. So on the road, we have a medium, we call it the road. On the Wi-Fi, we have a medium, we call it the channel. Okay? That road has a size. Usually, the bigger the road is, the more car you can have. Same thing on the Wi-Fi. We have a bandwidth. The larger the channel, the more data we can push through. And then on the road, we have cars. So usually, they're carrying people. On the Wi-Fi, we have frames that are carrying data. Okay? And to kind of measure how fast the cars are going, we're using that speed concept, which is a ratio, how much distance are we traveling in a given amount of time. And we usually express that in kilometers per hour or miles per hour. On the Wi-Fi, we call this data rate, right? How much data are we able to transmit on a given amount of time? And here it's also a ratio, and it's just the bits, the amount of bits that we actually able to send through the channel in a given amount of time, usually seconds here. And in both cases, we can actually use that information to calculate how much traffic the road can handle and how much traffic the Wi-Fi channel can handle. So if we focus on the Wi-Fi a little bit and on the data rate, if we think about it, if we want to understand how the data rates are calculated, we don't need to look at millions of different things. We need to look at the bandwidth that we have available. We need to look at the data we're sending, so how we're going to encode that data. And we're going to go into more details. And we need to look at this over time to create our ratio. So if we were to create like a simple formula to explain what a data rate is in Wi-Fi and how to calculate the data rates, it would be a ratio, right? A data rate. And at the top, we would have whatever we would need to calculate the amount of data we're sending. So that would be the bandwidth, taking into account the bandwidth and the data. And at the bottom of that ratio, we would have the time. Okay? So in its simplest form, this is how we calculate data rates in Wi-Fi. We're trying to understand how much data we're sending, and we're taking this information and we're looking at it over time. Okay? So let's look at each of these elements in a little bit more details with numbers. And everything we're going to talk about today is based on the standards. Okay, so don't blame me for the acronyms. And I've only looked at OFDM and OFDMA because this is mostly what we use today on our networks. So if we look at the bandwidth, right, the size of our Wi-Fi channels, you guys know that we can have different sizes. I've just kind of represented our communication channel as this big, rectangle. Depending on if you're using OFDM or OFDMA, you're going to find different terms. We call it channel or resource unit. And we have different sizes, right? It goes from 20 to 160 for OFDM, from 2 megahertz roughly to 320 with OFDMA. So that's our channel, our roads with different sizes. That road is divided into different subcarriers, right? Actually, in the standards, they're using tones for OFDMA and subcarriers for OFDM. So we subdivide that road into like different lanes. You could think it that way. So the larger the road is, the more lanes you're going to have to be able to send data on. And then there's, to understand the size of these lanes, we actually have two different set of sides. For HT and VHT, we have a 312.5 kilohertz size. So that gives us 64 subcarriers within 20 megahertz. And for HE and EHT, we actually have a size that's one quarter of that. And so we can actually fit 256 subcarriers into 20 megahertz. Now, what we care about is the data rates, right? So when we look at the subcarriers, not all subcarriers are equals, right? Some of them carry data, some of them do not carry data. So here you have the representation of a 20 megahertz wide channels. You can see that we have some data subcarriers, the blue ones, but we also have some pilots and some null subcarriers. What we care about is only the blue ones. I've also represented here a 26-tone RU, which is the smallest RU that's defined in the standards. And same thing here, you can see that not all subcarriers are data subcarriers, or I should say not all tones are data tones. Two of them are pilots, okay? So what we care about when we calculate the data rate is actually the number of subcarriers carrying data. They call it the data subcarrier, okay? So here, if I want to calculate my data rates, I need to understand my channel width. I need to understand if I'm using OFDM or OFDMA, and then with that information, I can go in the standards, and it will tell me how many of these data subcarriers I have in that channel bandwidth. Okay, so I have a little slide here to kind of go over these numbers. And you can see that here we get introduced to the first acronym that we have in the standard that kind of allows us to track all of these metrics, all of these variables. And the number of data subcarriers, they call it the NSD, and the NSDU for the resource units in OFDMA. So if we look at OFDM, these are the numbers we have in the standards, number of data subcarriers per channel width. And then you have the same thing for OFDMA, number of data tones per resource units. And you can kind of see the numbers. It makes sense. The larger the channel will be, the more data subcarriers will have to carry data on. Here, I've tried to include Wi-Fi 7. If you watch my previous presentation from Prague, you'll notice that I've omitted all of the multi-RU sizes because it makes it a little bit more complex. But you can go watch that video if you want to get that information. So the bandwidth in our formula, we could actually replace it by that number of data subcarrier, that NSD. Now, if we look at the data that we're sending over, in Wi-Fi, we're not just sending the bits like this. We have to modulate and encode these bits. So we have to also take that into account in calculating the data rates. So which data variable will actually impact the data rate? We have three of them. The first one is modulation, right? So modulation will impact how many bits we can actually fit in those subcarriers. In the standard, they have this term called the number of coded bits per subcarrier. I know the acronyms doesn't fit what I'm saying, but trust me, that's what it is. Then we also have the coding rate, right? So we're going to add some sort of encoding to the bits we're sending over the air. So this is representing as the R variable in the standard. And finally, we have the spatial streams, right? Spatial streams, it's just represented as number of spatial streams. And this one will also impact the data rate because more spatial streams will have, the more data we'll be able to send across the channel. So if we look at the modulation first, modulation is what we use to convert the digital bits into like something we can send on the radio waves. And We have different modulation techniques we use in Wi-Fi. You guys probably know them. And here, the bit that's important for the data rates is that the more complex the modulation technique is, the more bits we're going to be able to pack into that symbol, that OFDM symbol. So you have the numbers here from the standards. Keith has an amazing video on YouTube where you go through how all of this works, so you can watch this out. But these are the numbers we're going to use for the modulation. And then we have the coding rate. So in Wi-Fi, we're not actually sending all of the bits we're getting from the upper layer like this. We actually encode it to build some sort of resiliency in the wireless link. And that also impacts the data rates. This is representing as the coding rate, R. And these are the numbers specified in the standards. Maybe you've seen these numbers in the MCS table if you looked into the different lines. And so here, if I have a coding rate of 3/4, this means that I'm sending 3 data bits every time I'm sending 4 bits. So I'm losing a little bit of data here, of efficiency. That's why we have to take these numbers into account when we're actually calculating the data rates. Okay? So we have modulation, coding, they go hand in hand. You've seen the MCS table. That's how we can actually visualize all of these different options. And then we have the number of spatial stream. This one is pretty simple. If I have 2 spatial stream versus 1, I can pretty much double up the amount of data I'm sending across the channel. Okay? So these are just the numbers in the standards and the different numbers we have available from the standards. So the data, we could actually replace it by multiplying the number of coded bits per subcarrier with the coding rate and with the number of spatial streams. So far, so good? Following the math? Awesome. And then we can look at time. So to look at time, what we can do is we can zoom on one of these subcarriers and try to understand how we're using that subcarrier over time. All right, so that's what I've tried to do here. You can see at the top, I've represented our subcarrier from like a frequency standpoint. We can see it's 312.5 kilohertz wide. But if we zoom on it and try to understand how we're using that resources over time, you can see that, I'm going to try to attempt this. Oh, it works. We're actually going to send our encoded bits. So this is what we call the OFDM symbol. And we have a defined time to do this, 3.2 microseconds. And then we have to wait a little bit before we start sending the next OFDM symbol. And this little time in between is what we call the guard interval. All right? And for the guard interval in OFDM, we have 2 options. We have 0.4 microseconds and 0.8 microseconds. And we can just keep on sending the OFDM symbols like this on the different subcarriers. And remember, we have a lot of subcarriers in parallel, so we're doing all of this in parallel. So this is for OFDM. Now, if we look at OFDMA, actually it's not OFDMA. They changed it for HE, which is a little bit confusing, but for HE and EHT, they actually changed the size of that subcarrier, of that tone. So you notice that it's one quarter of the size that we used to have. So I'm able to fit 4 tones into the subcarrier we had above. But now, if I want to send the same amount of data, the same OFDM symbol, I'm going to need more time to send it over because I have a smaller channel bandwidth to do it. Okay, so that's why you'll notice that the OFDM symbol duration here is 4 times what we used to have. So we end up with 12.8 microseconds versus 3.2 microseconds previously. Okay, and the guard interval also, they introduced new guard intervals, and they actually introduced 3 options here. We have 0.8, we have 1.2, and we have 3.2 microseconds. So we can take these numbers, the time it takes to send the OFDM symbols and the guard interval to actually bring that into our calculation under the time ratio. Okay, so I can bring that at the bottom into my time ratio. And now we're starting to have something that kind of looks like a formula, right? And we can see that we are taking into account all of the different variables that will impact our data rates. So if I take this and then I add the operators, I can do something like this, where at the top I'm just going to multiply the number of data subcarriers by the number of coded bits per subcarrier, by the rating, the coding, and the number of spatial streams. and I can divide that by the time that it takes to send that symbol, which would be the symbol duration time plus the guard interval, right? And I'm getting pretty much, the formula that we're using in Wi-Fi to calculate the data rates. I can just make it look like it's something, out of a math class without colors, right? And this is the formula, right? So going back to what I was saying at the beginning is, it's not rocket science, it's just science. It's just about understanding what we have in this formula. And just to wrap it around, I've added the colors. So we have the bandwidth. We take into account the bandwidth. The larger the channels, the more data we'll be able to send. We then take into account the modulation, the coding rate, and the spatial streams. We multiply all of this, and then we divide it by how long it takes for us to send that data across the channel. Make sense? It's very quiet, so thank you for listening to me. I wasn't sure about doing a math presentation on the last day, but... Okay, so now that we have the formula, what do we do in math class once we have the formula? We apply it, right? So I came up with a couple of examples. I didn't want to do 10 minutes of examples, so I did one for OFDM, one for OFDMA. But you can go back to the MCS table and just play with the different numbers if you wanted to do it for yourself. So first example, we're going to try to calculate data rates for communication over 20 megahertz wide channel, modulation of 256 QAM, coding rate of 3/4, one spatial stream with a guard interval of 0.4 microseconds. Okay, I've just chosen those numbers arbitrarily so we can have something. So if I replace that formula with these numbers, well, the NSD, the number of data subcarriers on the 20 megahertz wide channel is, I'm starting with the time. Okay, so let's start with the time because that's fixed, right? So we're gonna, you notice it's not into my different variable except the guard interval. So we'll start with the time. We have 3.2 microseconds plus that 0.4 microseconds for the guard interval. We can put that at the bottom. The 3.2 comes from the fact that we are looking at the OFDM data rates, okay? Then for the bandwidth, in a 20 megahertz wide channels, we have 52 data subcarrier that we can use. For the modulation, if I'm using 256 QAM, I'm encoding 8 bits. I have a coding rate of 3/4, so I can just put that into the calculation. And then I have a spatial stream of 1, so I'm just going to multiply it by 1. Okay? If we do the math, we have something that looks like 86.7 megabits per second. Make sense? Example number 2, OFDMA. So here with OFDMA, we're going to have a difference for the duration, the OFDM symbol duration. That's why we had to create a new table for when OFDMA came around because of this. And then we have, in this case, a channel width of 484 tones, which is the equivalent of a 40 megahertz wide channel. Then we have modulation that's 1024 QAM, coding rate of 5/6, 2 spatial stream in this case. And I've chosen a guard interval of 0.8 microsecond, which is the shorter one you can get on these communications here. So we can start with the time with the longer OFDM symbols and the longer guard interval. And then at the top, I can define the number of subcarriers that I'm using to send data on, the modulation technique. So with 1024 QAM, we get a little bit more. And then I can multiply my coding rate and my number of spatial stream. And if we do the math, we end up with 573.5 megabits per second. So my presentation was supposed to be 20 minutes, and I'm happy to see that I'm like on the second. So, and then Keith asked me, "Do you want to do 30?" I was like, "Sure." And so I was thinking, okay, what can I do to kind of extend my presentation a little bit? And you guys know I like to dabble around with Python and create applications and stuff. So I was like, okay, what can I build to kind of illustrate what we're doing here and something that you guys can also use at home? So I built that a little Wi-Fi data rate calculator, and my goal was to kind of simplify a little bit the MCS table, because sometimes when we're trying to understand data rates for one specific client, we have to go to the MCS table, we have to look at the columns, the lines, and we have to kind of find that specific cell that we care about, and it's not always super easy to work with. So I've built this little app that just asks for a client device. It asks you which client device do you want to learn the data rates for, and you can just select it. So I'm going to select iPhone 13. And then it asks you, okay, which channel width are you using in your infrastructure? So I'm going to say 40. And then it just calculates the data rate supported by that device and spits it out into a small MCS table. And it gives that to you, and you can kind of study the data rate for that given device. If I only want to see the 2 spatial streams, I have even a smaller set for this device, and I can kind of look at these data rates. It's a little bit more convenient to do so. And I can study different devices here. I even added the iPhone 16. I know it's not out, but it's in my application. And guess what? It supports Wi-Fi 7. So I don't know. We'll see. I wanted to add the Wi-Fi the Wi-Fi 10 version for Peter, but I didn't have time. Maybe one day. But I can take and I was asking on Slack, what type of clients do you see in your infrastructure? I was kind of building that little database of client devices. So I got people coming back with Zebra devices. So, this is a Zebra MC40. This one, actually, if I go back and do it, I think this one only supports 1 spatial stream. We'll do 20 megahertz. This one only supports 1 spatial stream, and it's also HT, so it's a 11N. And you can see the data rates that you're getting. Here you can see the max you can get is 72.2 and 65 megabits per second. So anyway, that's a little tool I built that kind of creates this. This one is running locally on my machine, but we have something online that I'll share with you guys if you want to use it on your own. That's it. And this is a QR code to my LinkedIn. Yeah. Thank you.